In this video, we have a company that's trying to choose between 8 major projects. They cannot embark on all projects because they don't have enough staff and they don't have enough budget. So our question is, which project should be chosen and what type of profit will this give us? In a situation like this, where you're trying to decide which projects are a go and which projects are not a go, the use of a binary variable is a very logical choice. So if we, for example, put 1 for each project, that means we're going to take on all 8 projects. And in that case, let's figure out our profitability. It's going to be some product of these. So we'll make a total of $369,000. And let's look at what our expenditure will be like. And our total expense is going to be some product of this with this. And in fact, if I just make this absolute, then I can copy paste this down, but then this one's not gonna have. As you can see, if I try to complete all the projects, I will make a lot of money, but I'll be over budget and I'll need more than the staff available. So then which project should be chosen so that I maximize my profit while making sure that I'm not over budget and I'm not using more staff than that's available? Now first, I want you to look at the profitability of each project, the expense level of each project, and also how many people each project use, and see intuitively if you can decide which projects are more likely to be chosen and which projects are not. For example, let's compare 2 projects. If you look at these 2 projects, project 7 will give you more profit, but it also costs you more. It also uses more people. So between project 7 and 8, try to decide which one is more likely to be chosen. And try to expand that kind of logic to the entire set of projects before you optimize the problem. Now if you're ready to optimize the problem, you go to the Solver platform ribbon, you click on the model dialog box. Now we're gonna add our objective function, which is going to be our total profit. We have variables from C5 through J5, and then we have constraints here, the normal ones first, which says the left hand side here should be less than or equal to the right hand side. And I need to add one more set of constraints which says my decision variables C5 through E5 need to be binary. So I have my objective function, my variables, all my constraints. I'm now ready to optimize the problem by pushing the green button. And let's look at the solution we get. We are choosing to go with project 2, project 5, and project 6. The total profit is $199,000. We have $13,000 left over, which we will not be able to use for any other project, and we also are not using 18 staff members. So as you can see in this particular example, the money is a tighter constraint than the staffing. Now this is part A of the problem. Let's look at part B of the problem. In part B of the problem, it says the management decides that projects 2 and 5 are mutually exclusive, which means you cannot undertake both. So how can we model this? What you can do is you can tell Solver this is 1 and this is 1, but they cannot be 1 at the same time. If you think about it, if they're both 1 at the same time, then the sum is 2. Otherwise, the sum is going to be 0 or 1. So what you're going to say is, well, the sum of these two, the sum of D5 and G5 should be less than or equal to 1. So when you say this, when you add this constraint to your formulation, what it will do is it will make sure that the sum of these two, D5 and G5, never exceeds 1. That way you can model this mutual exclusiveness. Let's go ahead and add that to our model. I click on model here and I go to constraints, I go to normal, I say add, and then I'm going to say, I'll make sure that this left hand side is less than or equal to this right hand side. I'm going to hit OK. I'm going to resolve my problem, and let's look at our solution now. Now I'm undertaking 1, 2, 3, and 7, and before I was taking project 5 as well, but since I'm taking on project 2, I cannot take project 5 because of this constraint. So that models part B of the problem. Now let's take a look at part C of the problem, where it says, suppose that management also decides to undertake at least 2 of the projects involving consumer products, which happens to be projects 5 through 8. So you're saying, of these 4 projects, you would like to take on at least 2. Right now you're only taking on 1. How do you manage that? How do you model that? You say sum of these 4, 0, 1 variables should be at least 2. So that way you will ask solver to make sure that this sum is 2 or more. So right now it's only 1, so it'll have to come up with a better solution. You'll have to come up with a feasible solution. So we go to model. We have our original constraints. Now we're going to add one more constraint that says this left hand side is greater than or equal to this right hand side. Hit OK. We solve the problem. As you can see, now I'm taking on projects 1, project 6, and project 7. Note that each time I add a new constraint, the profitability slowly goes down. And that's true for all optimization problems. When you add more constraints to a problem, the profit will never improve. It will either stay the same or go down. So as you can see, binary decision variables helps us model situations like this where you have go, no-go decisions. And in addition to that, it also gives us flexibility to add some logical constraints that would be hard to do otherwise.